Hi, today I'm going to compute or explain how to compute THH of the integers. The idea is to first use fracture squares to compute, to reduce it to a computation of THH of the p-adic integers. And then THH of the p-adic integers is computed by reducing the computation to a relative computation where we work relative to a uniformizer. And that then follows from a relative version of Böckstedt periodicity, which we prove. The lecture today will not be relevant to follow the rest of the course, so we'll not go into computing TC of the integers in this course, but it might be very interesting since, after all, the integers is the initial ring. Hi, I'm Thomas Nikolaus from Mathematics Münster. Right, so the result we want to prove today is the following theorem, which is also like the computation of THH of the FP, of the field FP. It's also due to Böckstedt. And the result is that we have an isomorphism of THH star of the integers isomorphic to z for star equals 0, so it's a z in degree 0, then it's going to be a z mod n in degree star equals 2n minus 1. So for example, it's and I guess I should finish 0 else. And this means it starts in degree, for n equals 2, in degree 3 with a z mod 2, then we have in degree 5 a z mod 3, z mod 4, and so on and so forth. Okay, that's the theorem. And let me immediately say, in fact, a somewhat, in my opinion, nicer way of saying that. For example, I guess you could wonder, we know THH star of the integers is a graded commutative ring. But unfortunately here, what is the multiplication? I guess in degree 0 it's a z, so it's a multiplication on the integers. But then, all the classes here are odd degrees. So if you multiply two of them together, you land in even degree, so it's 0. So there's no non-trivial multiplication on that. But one can say a little more. In fact, this THH star, z, is the homology of a certain DGA of the differential graded Z algebra given by, so maybe I write it, THH star of the integers isomorphic to the homology of the DGA given by Z adjoint X tensor an exterior algebra on a generator E, where X sits in degree 2, E sits in degree 1. So this means a polynomial ring on this degree 2 generator, an exterior algebra on this degree 1 generator. And with the differential, this is a DGA and it has differential, which is partial X equals E and partial E equals 0. And that, of course, determines it because it's a DGA, so by the Leibniz rule. Okay, so that is this statement. And the statements are equivalent. Why is that? Well, let's just evaluate the homology of this DGA. How does it look like as a chain complex? So this is, of course, positively generated. So I guess somehow this is the degree 0 part generated by 1. And then it's 0 in negative degrees, and then we have the degree 1 part, and the only thing in degree 1 is E. So we have Z times E. And what is the differential? The differential here is 0, right? Because the partial of E is 0. And what about degree 2? Then we have Z times X. And here we have the differential given by the identity. So it sends X to E. And then the next term is EX. And here the differential again is going to be 0, of course, because I guess because of the Leibniz rule. You can just work out what the differential here is, I guess, the derivative of x times e, which is e squared. And in this DGA we have that e squared is 0. And then the next term is going to be generated by x squared. And again, by the Leibniz rule, we have that the differential of x squared is just 2 times ex. So we have multiplication by 2, and then this continues having 0, and then the next thing, map is going to be multiplication with 3, and so on and so forth, all by the Leibniz rule. And so immediately we see that we get this homology. And so at this point, this just looks like a convenient way of stating this result. And in fact, the reason this happens is that this DGA actually arises as through a spectral sequence. But one can actually show more. One can show that in fact, THHZ is as an E1 algebra, i.e. associative algebra, as an E1 algebra over, I guess I should say maybe HZ. I will, as usual, sometimes skip the H and confuse the integers with the Eilenberg-MacLane spectrum HZ. As the E1 algebra over HZ given as, I guess, by this DGA. I guess, strictly speaking, I should say by the homology, not the homology, the Eilenberg-MacLane spectrum of this DGA. It's partial, right? So a DGA in particular gives an algebra in the derived category of the integers. And then, so applying the Eilenberg-MacLane spectrum gives us that this is an E1 algebra in mod HZ. And that's a deeper statement. We will not prove that today, but one can show that this is true. And as a consequence of either the methods that prove this result here, or as a consequence of this slightly deeper statement about this being as an E1 algebra, this DGA, we get of either of these results, I mean either, well, of this, let me just say this, and this might mean either this result or the methods that lead, I mean that we discuss for today to prove this result. We get that we can try to compute THH of the integers modulo p, right? And that's a co-fiber of multiplication with p. And because of the fact that we have a lot of torsion here, p is going to be prime, of course, this is going to be interesting. And in fact, this is a ring. Why is this a ring? Because we can also write this as THH of z, and then tensor over HZ with HFP. Right? This uses that THHZ is actually an HZ module. And then we get that actually this is isomorphic to the is isomorphic as a ring, as a I should say the homotopy groups of that. As isomorphic on homotopy groups, topy groups to the homology of the DGA, and this is a DGA over FP, FP adjoint X, tensor lambda E, and then also with the differential partial X equals E and partial E equals 0. Okay, and this homology actually has non-trivial multiplication, and as a first exercise for today, I ask you to compute the homology of this DGA. And I mean, I guess in this case, this is really just a tensor product over FP. This is an exterior algebra over FP. So compute the homology of this DGA as a ring, and you'll see that in the mod P reduction on THH of the integers, you'll have non-trivial multiplicative structure. Which somehow tells you way more than just saying, I mean, this doesn't have any non-trivial multiplicative structure, but it's a very good trick in general if you have a sort of ring spectrum, and the homotopy for degree reasons doesn't support any multiplicative structure. If you take the mod p reduction, then very often non-trivial multiplications will show up. Similar things, for example, happen in K-theory finite fields. And now we want to prove the theorem I had on the board previously, Bergstedt theorem, and about the calculation of THH of the integers. And the idea is to split that up into a computation 1 prime at a time. And this uses generally the fact that you can recover a spectrum from its p-completions and its rationalization. And let me give some definitions in order to fix notation. And so for a ring spectrum, a ring I guess, or a ring spectrum R, we define. So the first thing we want to define is THH R with ZP coefficients. And by that we just mean the p-adic completion of THH R. Now that's a p-adic completion. If you don't know what the p-adic completion of a spectrum is, I have recorded a companion video in which I explain the notion of p-adic completion, which you can find in our theories on higher algebra. Okay, so this is the p-adic completion, and then I also introduced the notation THHR with Q coefficients, and that is just supposed to be the rationalization. Again, this notion is also explained in this companion video. And finally, there's also a thing showing up in the fracture square, which I denote THHRQP, by which I just mean take the p completion. So in other words, this guy, and then you rationalize this. And of course, in the p completion already all primes except p are invertible, so this is the same as just inverting the single fixed prime p. Okay, so and then of course the reason to introduce this terminology is that now we have a square. We can sort of recover the spectrum THHR by means of the Hasse-square from all its p-adic completions, where p ranges through all primes. And its rationalization. THHRQ, and then of course you have the maps into p prime, THHRQP. And as a warning, this notation might be a little bit confusing if you know, I mean, there's also something which we don't need in this course, but THH with coefficients, and this is not quite the same. So don't take this kind of CP, Q, and QP too literal. It's just notation that we'll need and that will come convenient. And of course, if we just put a star here, as usual, this just means the homotopy group of this spectrum. And in general, of course, one might wonder how to compute these guys. How does, for example, what does the p-adic completion of THH really depend on? And that is clarified by this lemma, which that we have that the p-adic completion of THHR actually only depends on the p-adic completion of R. So it's the same as the p-adic completion of R, and then also again you have to p-complete. And of course, the p-adic completion of R is again a ring spectrum if R is a ring spectrum. So that's what this means here. And this just takes THH as a ring spectrum, but you could also take THH of the p-adic completion. Well, let me just say, if say that once I prove it, you could take THH of the p-adic completion also in the p-adic world, which would be just take Hochschild homology, or maybe, yes, I write it like this, you would take Hochschild homology of this RP in the category of p-complete spectra. Okay, well that's the first statement. And the second statement is that the rationalization of THH, so THH are with Q coefficients, this is the same as THH of the rationalization of R. And then also with Q coefficients, but that is, so the claim is this is the same as this relative HQ. And remember that rational ring spectra, or the category of rational spectra, is just equivalent to the derived category of Q. So this is in fact under this identification, this is also just Hochschild homology of that corresponding E1 algebra in the derived category of Q relative to Q. Where here abusively I don't distinguish between the rational ring spectrum and the object in the derived category. Okay, how do we see that? And what's the first statement? For the first statement, you basically just expand what the definition is. A THHR with coefficients in Vp, that is just the same as the co-limit. So that is THH of the cyclic bar construction. So R, then we have R tensor R over the sphere, 3 copies, and so on. And then on the outside we p-complete. That's the definition. But of course, from the way that co-limits in the p-complete category are computed, we see that this is actually the same, or from the fact that the p-completion commutes with co-limits, we see that this is the same as can just also p-complete on the inside as well. You can first p-complete, then take the co-limit. So you have this guy, and then you want to p-complete this summand, this factor, and so on. And then you have to p-complete on the outside again. So that's the same. And then finally, of course, you can also pull the p-completion through and just p-complete all the single terms. RP, tensored over S, RP, and so on. And then in the end, you're going to p-complete again. But this is then exactly the same as THH of the p-completion with p-adic coefficients. Okay, that proves the first equivalence here. For the second one, we just note that we could as well just have written this term as the tensor product in the p-complete world, right? This is the p-complete spectrum, and it is the tensor product in the p-complete world. By the way, the tensor product of p-complete spectra is defined. So then just, if we do that, then we immediately get this right-hand term. The important thing is that the p-completion of THH only depends on the p-completion of the ring spectrum. And to see the second statement, we invoke a similar trick as before, just for the rationalization. We just say that THH RQ is just, by definition, the same as taking THHR and then tensoring over the sphere with the Eilenberg-MacLane spectrum over the rationals. But by our base change formula that we've proven in the previous lecture, this is the same as THHR tensor the sphere HQ relative HQ. Right, that's because of the base change formula. And that then, of course, is just, this term is just by definition the rationalization. HQ. Whereas the second equality here just follows from the equivalence of categories between HQ modules and the derived category of Q. Okay, so again, the upshot is that the rationalization of THH only depends on the rationalization of R. And then of course THH with QP coefficients is just a rationalization of this guy. Okay, so that is the fracture square we'll need, and as an example, so remember we're still on the mission of computing THH of the integers. We can already see what the rationalization is now. So the rationalization of THH of the integers is now just given by the Hochschild homology of the rationalization of the integers relative Q. So it's going to be Hochschild homology of Q relative Q, right? Because rationalization of the integers is just Q. And so this is actually the Eilenberg-MacLane spectrum Q, concentrated in degree 0. So this way we have already computed the rationalization of THH. And so in order to finish our fracture square, what we need is we need to understand the p-complete homotopy type of THH. And that is the next result, which I'll call Theorem 2. And this is also due to Bergstedt. And that states the following. That states that THH of the integers p-completed. This is given by the p-adics for star equals 0 and the p-adics mod n times the p-adics for star equals 2n minus 1 and 0 else. And of course I could say what this is. This only depends on the p-adic valuation of n, right? So, I mean, this is going to be z mod p to the kz, where k is the p-adic valuation of n. And this is, again, the homology of a DGA, and it's just basically the same DGA. You just do zpx, tensor lambda e, and then with the same differential, partial e equals 0 and partial x equals e. Okay. And obviously, if we have our first theorem, the integral computation of THHD, then by the fact that all the groups have bounded order of p-torsion, the homotopy groups will just p-complete, and you immediately see that this result here follows from the first result. But the converse is also true, which I will show now. So proof of theorem 1. So our first theorem about THH of the integers from theorem 2. And it's the wrong sheet. So I guess if we assume theorem 2 from theorem 2, we get that, I mean, we have the computation of THH of z with the p coefficients. We can read off what THH z with qp coefficients is. Right, and what is it? Well, I guess it's just a rationalization by definition of this guy. So in degree 0 we get a copy of qp and then we get 0 everywhere else, because this is just torsion. So it's going to be an Eilenberg-MacLane spectrum on the p-adics qp in degree 0, and thus the fracture square takes the following form. We have THH z, and then this maps to the product over all primes THH z with p-adic coefficient, zp coefficients. And then we have the rationalization. We've just previously seen that the rationalization is an Eilenberg-MacLane spectrum concentrated in degree 0. And that is an Eilenberg-MacLane spectrum, product of Eilenberg-MacLane spectra over all primes, also concentrated in degree 0. And so you see that these two terms, I mean, by the long exact sequences associated to that pullback square of spectra, you see that these two terms only differ in degree 0. So we immediately get that in degree 0, this is just given by the profinite completion of the integers, a product over all zp's, and this is z, and this is the same difference as here. So we get immediately that THH 0 Z is actually Z. I guess we had already known this for quite a while, but we get it nicely back here. But then also we see that in higher degrees, THHN Z is just the product over all primes of THH N Z ZP for n larger 0. And that is, of course, then the same as the product over all p prime of Z P mod N ZP. And that is, of course, Z mod N Z. Okay, so that is how we can deduce theorem 1 from theorem 2. And what I will do now is I will prove theorem 2. And the strategy is roughly to first prove a relative version of theorem 2, where we work relative to the prime p. And then we are going to invoke some descent style trick to deduce something about the absolute statement from the relative statement. What do I mean by relative statement? Relative statement just means working relative to another base ring spectrum than the integers, than the sphere. And the ring spectrum we will work to relative is the following. So we define a commutative ring spectrum. I mean, by commutative we shall always mean E infinity. We're not working with anything less structured. A commutative ring spectrum S adjoint Z, so which is just by definition the spherical group ring of the natural numbers. And this is defined to be just a suspension spectrum of the natural numbers. So as a spectrum, suspension, I mean the natural numbers, where I guess I should say where the natural numbers n is considered as a commutative monoid or commutative algebra in the infinity category of spaces with respect to Cartesian product. Right? I mean, this is in fact, of course, a commutative monoid in sets with respect to Cartesian product, but then I consider it as a discrete space. And of course, as a space, it's just a disjoint union of points. So as a result, this is just going to be a disjoint union of copies of the sphere spectrum. But from the fact that this is a commutative monoid and the suspension spectrum functor is strong symmetric monoidal, we get an induced commutative ring spectrum structure on that guy. And that is what I shall mean by the notation S adjoint Z. It's also sometimes called the flat, I mean, I guess the flat adjoint Z or the flat A1 would be the spectrum of that in derived algebraic or spectral algebraic geometry. So to give a discrete module, discrete ring, commutative say ring R, the structure of an A mod, of an S adjoint Z algebra is equivalent to giving an element pi in R, right? So that we send Z to pi. And why is that? I guess in order to do that, we have to write down an E infinity map. So we want to make it a commutative, we want to make R a commutative algebra in the category of SZ modules. So we have to give an E infinity map from SZ into R, into the Eilenberg-MacLane spectrum HR. But because this guy is concentrated in degree 0, such a map, giving such a map is the same as giving a map from the Eilenberg-MacLane spectrum of pi 0 of this guy, which is this. So giving such a map is equivalent to giving such a map, but such a map is just a map of rings from Z adjoint Z to R, which just amounts to giving the element pi. And I want to now consider the integer z as an SZ algebra. I want to consider the integers as an algebra over SZ by sending z to p. So that is my element pi, in this case is going to be p. And let me immediately issue a warning. If we consider a ring spectrum, say commutative ring spectrum, R instead of a discrete ring, then an E infinity map from SC into R is not the same as an element Z in pi naught R. Of course, I mean, giving R the structure of an commutative algebra in the category of SZ modules is equivalent to giving an E infinity map SZ into R, but this is not equivalent to giving an element Z. Of course, whenever you have such an E infinity map, you can apply pi naught and you will get an element in pi naught R, which is pi, but this is not enough. I mean, in other words, SZ is not the free E infinity algebra on Z, on a single generator. While, of course, the integers adjoint Z is the free commutative ring on one generator. Well, that's one of the aspects where higher algebra highly differs from ordinary algebra. One can, in fact, write down a formula for the free E infinity algebra on a single generator, and this looks horribly complicated. You'll have contributions from the stable homology of symmetric groups. Yeah. Okay, so I guess this is the warning, but we'll work with discrete rings, and then it's easy to give discrete rings the structure of an algebra over SZ. And I mean, maybe I should say here, SZ is free than an E1 algebra though. So giving something, giving an E1 map from SZ into R is literally giving an element pi, but then lifting that to an E infinity map, which, as we know in higher algebra is extra structure, is complicated. Okay, good. So, but anyways, so now we know how to consider the integers as a algebra over SZ, and so we can formulate a relative version of Bergstedt periodicity. And remember, Bergstedt periodicity was the statement that THH Fp was periodic in the sense that it's Fp adjoint X for X a generator in degree 2. So the name Bergstedt periodicity was suggested by Lars Hesselholt. Maybe it would be more correct to call it Bergstedt non-nilpotence, because the element X is non-nilpotent, but that of course doesn't sound as good as periodicity does. Okay, so what's the statement about relative Bergstedt periodicity? So the statement is that we have that THH star of the integers relative SZ. And this is again by sending Z to P. And then we want to actually, I mean, this makes sense now, right? Because this is a commutative algebra in SZ modules. And of course, then we also apply our standard notation that this just means the P completion of this THH term. So it's just the P completion of the underlying spectrum, which again then carries the structure as an algebra over SZ. because everything was commutative. This is the ring spectrum, and the statement is that the homotopy groups of that are just given by ZP adjoint X, where X is a generator in degree 2. So you see this takes pretty much the same form that Bergstedt periodicity takes, which was the statement that THH FP was FP adjoint X. And so there's two slight differences. The one is that here we have to work relative for the integers and we have to p-complete. But not working p-complete in the case FP wouldn't make a difference because THH FP is an FP module and hence already automatically p-complete. Okay, and I should mention that this version of Bergstedt periodicity has recently played a role in the work of a number of people. I guess was observed by Jacob Lurie. It played a role in the work of Bud Morrow-Scholze. It also appeared in a paper of mine with Ben Antio and Akhil Matthew, and in a paper of mine with Achim Krause. Okay, then let's prove this. So what we do is we consider the mod P reduction. So we consider the spectrum THH Z relative SZ with p-adic coefficients, and then we reduce mod P. So this is the mod P reduction as a spectrum. Remember, this is just a cofiber of multiplication with P. And the point is, because it's a module over the integers, as we've done before, this is actually equivalently written as tensoring over the integers with FP, right? So maybe I should write HC, HFP. And there is this completely confusing and counterintuitive fact that if you take an arbitrary ring spectrum and you reduce mod P, then it's in general not a ring spectrum anymore. It actually fails, for example, for the 2-complete sphere because S mod 2 has actually 4 torsion. But so if you happen to be an HZ module, then the mod P reduction can also be written as a base change from HZ to HFP, which obviously then is actually, again, a ring spectrum. And the point is here, this is also, in this case, the module structure over the integers actually comes from a module structure over SZ, or restricts to a module structure over SZ. So we can also write this actually as Z relative SZ, p-adic coefficients, and then base changed over SZ to S, right? So Z acts through the element P. So killing the element Z is equivalent to killing the element P here. And the point is now we can invoke our base change formula. So I guess we have proven this base change formula when we delete that and when the base was S. But it's true even for any base, and we can just p-complete at the very end by the way the p-completion of tensor products work. So what we get is this is the same as just taking Z, the base change, so maybe I write this out, Z tensored over SZ to S, and then working relative to the base ring spectrum S. This is just our beloved base change formula. And then here we automatically, of course, get that this is THH FP, right? Because this is just FP, and working relative to the sphere is just THH with p-adic coefficients, but I already said that this is actually just THH FP because this is already p-complete. So what does this mean? This means the p-completion of our spectrum actually has, we can compute the homotopy groups of the mod P reduction. Now we consider the long exact sequence. We study the long exact sequence, which looks as follows. So it goes from the homotopy group THH in degree, say in even degrees. Well, let me just write star. Z relative SZ with p-adic coefficient. Then we have the multiplication with P, goes to the same group. Z relative SZ with p-adic coefficients. And then we have THH FP, star FP. And then the connecting homomorphism goes to the THH group one degree lower. And here, I guess, this is not good board work. This ends here. The next term would be THH star plus 1 Fp. So what do we get? So I claimed that from this we can deduce that THH, this term, the homotopy groups of this term, so THH star Z relative SZ, P completed, is P torsion free and concentrated in even degrees. So again, and I want to post this as an exercise to check that from this statement, from this long exact sequence, you can deduce that this THH term, THH star Z relative SZ with p-adic coefficients, is concentrated in even degrees and P torsion free. And I guess as a hint, you should just contemplate even and odd degrees separately. So you want to prove by this long exact sequence, because we know that THH Fp is concentrated in even degrees, want to first argue that P is acts injectively, and then maybe argue why the odd homotopy groups have to vanish. Okay, but once we know that this is true, you also get a little bit more, namely you get that in degree 2, this map is surjective, right? Because the next term is odd, it's going to be 0. So this map is surjective, so there exists an element x in pi 2, THH2, of Z relative SZ p-adic coefficients, lifting the Böckstedt element in THH2 of Fp. Thus, we get a map from THH from ZP adjoint X into THH star Z relative SZ with p-adic coefficients, right? Just by sending this X to this lifted element, to lifting the Böckstedt element. So I'm abusively denoting all my elements by X. Of course, this is a lift of that. Maybe X tilde would be more appropriate. But let me not do that in order to avoid awkward notation. So we get this map, and this is which is an equivalence or an isomorphism after mod p reduction. Mod p reduction. And of course, all these groups are derived p complete and p torsion free, so it's an isomorphism. So an isomorphism. Okay, and that actually in turn proves the result of relative Böckstedt periodicity. Okay, and now that we have this result, actually we can go and prove our main result, except there's one little tool missing, which is what I call descent beforehand. So we have this relative result where we can compute THH of Z relative to SZ, and now the question is how do you deduce anything about the absolute? I mean, after all, we're interested in computing THH of the integers and not some funky relative version of THH of the integers. And the idea here is to use, again, our base change formula. So in general, and actually maybe I deduce everything I say without the p coefficients now, because it's getting a little bit annoying to write the ZP all the time, and then the same will hold also with ZP. So we get that in general we have THH R relative SZ. I mean, 2 videos ago I've proven that this is equivalent to THH R tensored THH SZ with SZ. Right? And now we play this trick that, of course, this is a module over R, and R is an ordinary ring, so it's actually a module over the integers, HZ. So we can write this whole base change also as sneaking in another copy of the integer. So we're going to write this as HZ, tensor THH, and we tensor over the sphere, of course, SZ. And then again, we sneak in the copy of the integer so that the two copies cancel out This is again over the integers THH. SZ. So once we sneak that in, we can just use the base change formula to deduce that this is in fact the same as Hochschild homology of Z adjoint Z, relative Z. This is just because we can pull that in, and then here again we get Z adjoint Z. And the thing is, we completely know what this Hochschild homology looks like, right? By the HKR theorem. This is just the de Rham cohomology, omega 1 of Z adjoint Z over Z. So in other words, this is just an exterior algebra over the ring Z adjoint Z on a degree 1 generator, dZ, which squares to 0. And what we do now is, of course, we can filter this spectrum by means of its Postnikov tower, or equivalently, in this case, by its HKR filtration. And that gives us a filtration on the spectrum THHR, in fact, which somehow with associated graded we can identify, and that gives us a multiplicative spectral sequence. Which takes the following form. There is a convergent, and I guess convergent I mean strongly convergent, multiplicative first quadrant spectral sequence, which takes the following form. It takes the form THH in degree n R relative SZ. This is just for any ring R. An ordinary ring though, we needed that module structure over the integers. Z adjoint Z with omega star, and I guess I should put omega m of Z adjoint Z relative Z. And it converges strongly to THH n plus m of R. And of course, this term we can simplify by what I just said. This guy is actually just an exterior algebra. So this term actually looks like THH star R relative SZ tensored over the integers with just an exterior algebra lambda on dz. Right? I guess the name dz now doesn't make sense anymore, but this just comes from the fact that this is a generator up here. And converging to THH n plus mr. And again, I guess I already hinted as to how you construct the spectral sequence. You just observe that THHR is the same as tensoring over this guy with HHZZ adjoint Z, a relative Z, and then you filter that by its Postnikov tower and you get the spectral sequence. Okay, good. So this is the last tool that we'll need. And what we're going to do is we're going to apply this now in the situation of the integers. And again, there's a similar spectral sequence if I p-complete everything inside. I just wanted to save some board space. Proof of theorem 2, which was the p-adic calculation of THH of the integers. So in our case, the spectral sequence we've just constructed, or at least indicated, takes the following form. So we have this term, this relative term, THH star R relative Z. So R is going to be the integers with the element Z going to P. This takes the form by our relative Bergstedt periodicity. This is just going to be ZP adjoint X. Right? And then we tensor over the integers with lambda dz. And I guess I should put, this is maybe going to be a p-adic integers. I mean, not that it makes a difference here, but it would be a little bit more logical to tensor over the p-adic integers here. And then this guy converges to THH star of the integers with p-adic coefficients. And let's draw the spectral sequence. So x has degree 2 and dz has degree 1. And I guess I've never really fully told you how the grading here works. So let me tell you that in this example. So here's how the spectral sequence looks like. And this is actually using so-called homological Serre grading. So on this axis, I'm going to denote the element x here. So denote that by a little box. And every little box is supposed to represent one copy of the p-adic. So this is degree 1, this is degree 2. There's the element 1 here. 1. And then here in degree 4, we have the element x squared. X squared. Then we have the element x to the 3 and so on. The odd elements here are 0. And then we're going to have the element dz sitting on that axis. Here's dz. Then here we have the element x times dz, and so on. X squared dz. And then the rest is 0. So this is degree 1 and 0 on this axis. So the whole spectral sequence is concentrated in this little strip here above the x-axis. And how do the differentials go? Differentials go like in homological Serre grading. So there's no d1 differential for degree reasons, but now we're going to have a d2 differential, a possible d2 differential, starting here and going there. And then here's the next d2 differential, and so on. And you see there can't be higher differentials. So in Serre grading, the higher differentials would go higher up. So the next differential would go up 2 steps and 3 steps to the left, and so on. But this can't exist for degree reasons. So what we deduce is there can only be a d2 differential here, and this is because it's multiplicative. So it's a multiplicative spectral sequence. The differential is going to be a derivation. It satisfies the Leibniz rule. This is by the Leibniz rule determined by the value on x, right? Because everything here is going to be powers of x. So d2 of x. And where does this land? This lands in a copy of the p-adics. So this is an element in the p-adics, or maybe let me write like this. Element in the p-adics times, I guess, dz. So it's a p-adic multiple of dz, so it's alpha times dz, where alpha is a p-adic number, right? And now let's look at what happens in degree 1. So by staring at the spectral sequence, you see that in degree 1, the only contribution can be this. So we get that THH1, maybe I should have said this, the total degree in the spectral sequence are just diagonals. So degree 0 will just be this 1 coming from the ZP, and then degree 1 will consist of this guy and that guy. Here it's 0, so it's only going to be this. So it's in fact a quotient of this, co-kernel of this differential. So THH1 of ZP relative, with ZP coefficients. I mean, I guess it's the same by what I said earlier, but let me keep writing Z. This is just going to be the same as take the p-adics and you quotient by this differential, which is alpha ZP. Right? This is by the spectral sequence. But then we also know, this is by what we said, proved earlier in the course, this is the same as H1 of Z, relative Z, with p-adic coefficients. But this is, of course, the same as the Kähler differentials, which is 0. So, or said it differently, Hochschild homology of Z relative Z is just concentrated in degree 0, so it vanishes in degree 1. Okay, so this is 0. But, well, if ZP mod alpha ZP is 0, then we conclude that alpha is a unit. And then we can, in fact, without loss of generality, by just changing x by a unit, we can just assume that alpha is 1. And then we deduce our calculation. Then we get the DGA description. There's no possible extension problems coming up in the spectral sequence. I mean, in every degree, we're just going to have a single contribution. No multiplicative extensions, of course. I mean, there's, after all, no non-trivial multiplication, and then we're done. All right. That finishes my proof of the computation of THH of the integers. Thanks very much for watching, and see you next time.